Hi, in this flip video I'm going to go over the workshop on page 18, which is a LeChat WS principle workshop. This is great preparation for your homework and for the quiz that you're going to have in class in LeChat WS principle. What we're going to be looking at here is the reaction that's at the top and how these different changes are going to affect it. You have to be able to do the direction of shift and also talk about increases and decreases in concentration. When we talk about changing something like where we add SO2, you will not have to answer that on the quiz, so that'll be blanked out. So where we add O2, same thing. Where we're adding SO3. So when you're talking about a particular reactant or product, you're not going to talk about the effect of concentration there or affect what happens if it increases or decreases, because you are altering that. So we're going to remember here for concentration and temperature, remember add, away, remove, towards. So two things to keep in mind as you're looking at concentration and temperature in terms of your shifting and what's going to happen to concentration. So if we add O2, or SO2, sorry, SO2 is right here. When we add, we shift away. So to shift away from that is shifting this way. So we are shifting to the right. As we are shifting to the right, what that's going to do, we're not going to talk about SO2, we don't need to worry about that. But since we're shifting away from O2, O2's concentration goes down. What's really happening here is by adding more SO2, it's going to react more frequently with O2, and it begins to use up the O2, essentially, it's in there. So if you think about the school dance way of looking at this, if you add SO2, that's like adding more girls, that used up the single guys in that gym. As we're doing this reaction, we're adding up that O2, we are increasing our amount of SO3. So by putting more SO2 in, it collides more frequently with SO2, thus increasing our concentration of SO3. So keep in mind your arrow of shift needs to make sense in terms of your concentrations. And since I'm shifting to the right, I have more of the stuff on the right side. I have less of the stuff on the left side. If I add O2, and again, I don't need to talk about O2, so I'm going to blank that out here. If I add O2, I'm going to add away, so I'm still going to shift in the same direction. So my direction of shift is the same. Now I'm using up O2, so SO2. SO2 and O2 are colliding more frequently, and when they collide more frequently, they're going to produce more SO3. If I add SO3, SO3 is on the other side of this reaction from the ones that we've been talking about. By adding SO3, I'm favoring a shift away, add away. So now I'm shifting to the left. I'm favoring my reverse reaction. By adding more SO3, there's more available to decompose. It will make more SO2, it'll make more O2. So you notice now that we're shifting to the left, we have more of the things on the left-hand side of the reaction. I'm not really worried about what's happening with SO3 since that's what I'm changing. Now let's talk about removing. So if we remove SO2, so if we remove this, when we remove, we shift towards. So it's really happening because we take that out. SO3 is still decomposing, but the O2 doesn't have anyone to react with to make SO3. So what really happens, we take out the SO2, it's basically like taking all the girls out of the dance. Eventually we'd end up with a whole bunch of single guys. So by removing SO2, we are shifting to the left. And as we are shifting to the left, we're not worried about what's happening with our concentration of SO2 because that's what we're altering. But we're going to have an increase in our O2. We're going to have more of that building up. And that makes sense with our directions of our arrow. If we shift to the left, we should have more of the stuff on the left-hand side. Because we're taking out SO2, it's not available to react with O2, not available to make more SO3. So the SO3 here is getting used up. We're going to have a decrease in our concentration of SO3. When we remove O2, so if we remove O2 right here, remove shift towards. As we're removing the O2, we're still going to have more SO2 forming. So SO3 will still break down and make more O2. But O2 and SO2 won't be able to react with each other and won't be able to form more SO3 to replace that. So by shifting to the left, and again, we don't have to talk about O2 here. By shifting to the left, we're going to start getting a buildup of our SO2 on our left-hand reactant side. And we are using up our product SO3, or our thing that's on the right-hand side. Last but not least, we're going to remove SO3. So when we remove SO3, remove, shift towards, so we're going to shift this way. And we're not going to talk about SO3 because that's what we're taking out. But because we're shifting towards SO3, taking this SO3 out means we can't make more O2 or SO2. So we're going to decrease our amounts of those. Now temperature, remember, functions the same way. So first we're going to talk about an increase in temperature. We find our heat term in the reaction, and it could be on either side, so you have to be cautious about this. When we add heat, we add temperature, since heat's over here, we're shifting to the left. That's going to favor the decomposition of SO3. So we're shifting to the left. SO3 is being broken down more frequently. So since we're shifting to the stuff on the left-hand side, we're making more of those products of decomposition, SO2 and O2. When we decrease temperature, we're doing the opposite. So we're removing heat. By removing heat, we are, remember, add away, remove towards, so we're shifting this way. So SO3 can't decompose as much when we don't have as much heat. So we're shifting towards the formation of SO3. We're going to begin to make more SO3. It's not going to decompose as quickly. It's going to build up. And SO2 and O2 will be decreasing because SO3 isn't breaking down to make them. The last two we're going to look at, we're not going to look at volume separately. We're going to look at pressure, however, increases and decreases in pressure. So when we are looking at our reaction, and actually to make this a little bit easier, I'm going to pause for a second and rewrite this reaction. I think this will make this a little bit easier to follow. When we're looking at things going on with pressure and volume, we have to look at moles of gases. So we find our G's, there's our G's, and we want to look at how many moles of each of these we have. So we have 2 moles of gas here and 1 mole of gas here. On this side of the reaction, we have 3 moles of gas. On this side of the reaction, we have 2 moles of gas. Some people like to draw a picture where they like to make the different sides look different sizes. So if you want to do that, it's kind of a nice little trick to do. You could say, okay, the side with 3 moles would occupy more space. So more moles of gas are going to occupy more space. At STP, 22.4 liters each. So this side over here has 3 moles. It would be larger than this side that has only 2 moles. So some people like to kind of do this, think about squeezing a balloon, how that would look. It can be a little bit helpful. So if we increase pressure, you can imagine if you increase pressure, things have to rearrange to a way where they're going to take up less space. So if you imagine squeezing this thing, if you squeeze this a lot, it would end up looking more like this. If you imagine squeezing a balloon, it would shrink. So if we increase pressure, we're going to favor the production of fewer moles of gas. So 2 moles of gas takes up less space than 3 moles of gas, so we shove everything together. We favor 2 moles of gas. So we're going to get more SO3 being produced because there's only 2 moles of it there. What really happens here, if you want to look at this visually, so we have SO2. It's not really an accurate picture, but we have 2 moles of this, and then our moles of O2 over here. So that's taking, it's arranged in a way that takes up a little bit more space. Whereas on the other side, because we have SO3, because there's more O's stuck onto the S's, there's only 2 of these guys, so they take up less space. So when we shove things together, they arrange themselves in a way to take up less space, and that's being organized as SO3. Meanwhile, our amounts of stuff that take up more room, our 3 mole side, are going to decrease. Now, when we decrease pressure, things are able to spread out. If you lived in a very, very big home, you wouldn't put everything you owned in one room. Spread it out throughout the house. So we're going to spread out our gases, let things kind of breathe a little bit, and we're going to favor having 3 moles of gas. So we favor a shift to the left. We have plenty of room to have 3 moles of gas, so we have more O2 and more SO2, and we're going to have a decrease in SO3. So hopefully this helped you prepare for tomorrow's quiz. It is very important. The quiz will be in this format, so make sure that you practice the examples on pages 19 and 20.